Presurgical orthopedic plates are widely used for the treatment of cleft lip and palate. In this work, we present an automated digital pipeline for the design of the plates, which are fabricated using 3D printing. The recommended inputs of our pipeline are intraoral scans. Here, we demonstrate our pipeline on a sample unilateral cleft lip and palate scan. We adopted DiffusionNet, a neural network for general 3D surfaces to predict the positions of 10 landmarks in a custom two-stage process for increased precision. Utilizing these landmarks, we register a segmented template to the input scan via the non-rigid iterative closest point algorithm. In the green area, the alveolar ridges are registered for a tight fit, while the lip cleft is bridged over by the yellow area to allow the ridges to grow together. The palatal cleft area in red is registered afterwards. We then start our plate generation by cutting the template down to the plate region and smoothing the potentially rough boundary. Before bridging over the palatal cleft region, we approximate the shape of a corresponding healthy palate by fitting a sphere. The optimal sphere minimizes its distance to the dark blue area while not penetrating any colored region. To ensure a smooth connection between the alveolar segments, the sphere is forced to touch both regions marked in green. The points in light blue are offset by 2.5 mm to keep a safety distance from the cleft tissue. We then bridge over the palatal cleft region for the plate by applying Laplacian smoothing. The resulting surface follows the sphere and thus imitates a healthy palatal shape. We offset the plate by 0.1 mm to avoid creating harmful pressure points. To minimize the triangle's self-intersections during offsetting, we use a custom selective Laplacian smoothing algorithm to reduce the curvature in convex regions. We offset a copy of the surface by a custom 2 mm thickness and apply the same convex smoothing to it. The user may place 2 additional landmarks to identify the course of the lip frenulum. We cut the plate around landmarks to avoid potential pressure points in this region. Finally, a volumized plate is created by connecting the 2 surface copies. A small number of selective Laplacian smoothing iterations remove the remaining irregularities. Users can optionally adjust the plates through a set of customizable parameters. For example, the plate thickness over different regions, distance of the palatal cleft, addition of artificial rugae as stimulation elements, and a ventilation hole. Cases with bilateral cleft lip and palate are handled almost identically. Another 2-stage DiffusionNet model, trained specifically on the bilateral cleft types, also predicts 10 landmarks using a similar scheme. We designed a separate template for bilateral cleft lip and palate scans. Since our passive plates do not cover the premaxilla, only the alveolar ridges are registered. Afterwards, the same sphere prediction algorithm applies for approximating a healthy palate's curve with a safety distance of 2.5 mm kept from the inner cleft tissue. Cleft filling around the sphere, as well as convex smoothing, used for volumization, work identically. Since the premaxilla is excluded, this plate does not require cutting around the lip frenulum. The same parameter adjustments are possible for bilateral cleft lip and palate plates. The University Hospital of Basel collected a large dataset of both unilateral and bilateral cleft lip and palate intraoral scans and digitized plaster casts. The pipeline and its parameters were optimized on this dataset in close collaboration with multiple cleft care professionals. Many parameters are still user adjustable, as already demonstrated. We evaluated our pipeline's performance on the following 12 printed models. 6 are unilateral and 6 bilateral cleft lip and palate. An orthodontist and a surgeon assessed all plates as suitable for patient use in most cases without requiring any subtractive adjustments. Finally, several patients are already undergoing treatment with our automatically generated plates. We want to thank the University Hospital of Basel, Switzerland, and Savitha Medical College and Hospital, India for their cooperation. The photos depict the first patient being treated in Basel with a 3D printed model of our automatically generated plate. The nasal stent was added post-print. We embedded our pipeline into a simple graphical user interface in Blender to extend its accessibility to the general medical community. No expertise is required for the usage, and the computations take only approximately 3 minutes. Thank you for watching.